Hey there, today we're going to take a look at changing temperature, but before we take a look at that, we're going to look through a little bit of a note on temperature. There are some key facts that you need to know in here, but not too much. A lot of this is a bit more of history and for interest's sake. For us, measuring temperature is quite trivial. You put a thermometer into the thing that you want to measure the temperature of, and you read the thermometer. Now, we didn't always have thermometers, and people used to make thermometers. So in order to make a thermometer, you need two known points. This could be, ice and the boiling point of water. It could be your body temperature and the temperature outside on a certain day. You just need two known points and then define how many divisions are between those 2 points. Alternatively, you could have one known point and a known interval. So you could say, right, ice is 0 degrees, and when I leave a cup of ice out for 2 minutes, it goes up by 1 degree, and that's what I'm calling 1 degree. So really, you just need two things to define a temperature scale. Either two known points and then divide it up in between, or a known point and the interval between points. So we've got these two handsome chaps that did define temperature scales. Do you know who they are? The guy on the left is German physicist Daniel Fahrenheit, and he proposed a temperature scale in 1724, which was called the Fahrenheit scale. Rather than 2 points, he actually used 3. He called 0 degrees Fahrenheit the temperature of a particular brine solution, so salt and water, and his second point was 32 degrees Fahrenheit, and this is a combination of ice and water, or the melting point of ice. While he could just use those two, he went on further to define a third point in his scale, which is the temperature of the human body, 96 degrees Fahrenheit. And then he divided up the scales between there. So the divisions from 0 to 32 degrees Fahrenheit and 32 degrees Fahrenheit to 96 degrees Fahrenheit weren't actually even, because going from that brine solution to water and ice, if you break that up into 32, it's not the same as going from ice and water to the human body and breaking up in the same intervals to go from 32 to 96. So knowing that that guy is Fahrenheit, you can probably guess that this guy on the other side is our Swedish astronomer, Anders Celsius. Now this was originally called the centigrade scale, but was renamed to the Celsius scale in honour of that Swedish astronomer, and he first came up with this scale in 1743. He set his first point at 0 degrees Celsius, the freezing point of water at mean sea level, which is specified to specify the pressure at mean sea level. And his second point, he decided to call 100 degrees Celsius, the boiling point of water at mean sea level. He decided to choose nice numbers, 0 and 100. Who doesn't like using nice numbers? But then this also gives rise to reasonable numbers for day-to-day weather. Like the poem my cousin taught me when I was little so I could understand the numbers. 30 is hot, 20 is nice, 10 is cool, and 0 is ice. So you could quite easily talk about the weather. They'd be nice numbers to talk about. Oh, today I needed my jeans and a jumper. It's probably about 10. Oh, today was absolutely gorgeous. I just went out with what I was wearing inside the house. It's about 20. It was boiling hot. I had to go out in my short shorts and tank top and I was still sweating. I wish I had a pool. I mean, they wouldn't have said that in 1743 because, they had to wear different stuff. But you'd understand that that's like 30 degrees. You'd understand these numbers. They would make a lot of sense. The other great thing that the Celsius scale had going for it is that it's based off water. From a science point of view of wanting to study the world, this is quite useful. 71% of the surface of Earth is covered in water, so why not have a scale that's based off water? Furthermore, if we were to talk about human science instead of natural science, adult humans are about 60% water, so it doesn't really matter if you're studying the natural world or if you're studying humans. It's a lot of water, so having a scale based off water makes a lot of sense. Even today, all but a handful of countries realise that it's the obvious choice. Or is it? What is temperature? Temperature is a measure of the average kinetic energy of the particles. So for physics, surely it makes more sense if we base a scale off of kinetic energy instead of water. Enter in this guy, Lord Kelvin. In 1848, he wrote about the necessity of an absolute thermometric scale, with infinite cold as 0. Now that sounds quite hocus pocus and a bit creepy, but let's actually give him some credit, look into what he's talking about. What do particles in a solid do? Hopefully, you thought vibrate. Particles in a solid vibrate about fixed positions. Now, if we cool the solid, the particles will vibrate less, and we cool it further and they vibrate less, and they cool it further and they'll vibrate less. Until when? Until the particles stop vibrating. After you've cooled it until the particles stop vibrating, you can't cool it anymore. You can't take any more energy out of that system. There's no more kinetic energy in that system. You can't take it out. And this is the concept of absolute zero. Note that in practice, it would take an infinite amount of energy to cool an object to absolute zero, and so it's just a purely theoretical limit. But this concept of absolute zero is significantly better than just having a random zero as your scale. But this is only one point. We saw earlier that in order to define a scale, you either need 2 points or 1 point and a temperature change. So because Celsius was fairly prevalent and based off water and makes a lot of sense from that sort of thing, Lord Kelvin decided that we'll just use the same divisions as degrees Celsius. No other value matters, just absolute zero. So if we choose degrees Celsius as our intervals, so there's 100 divisions between the melting and the boiling points of water, it'll make conversions easy between degrees Celsius and Kelvin. And that conversion is whatever you have in degrees Celsius, add 273.15 to it, and you'll get the temperature in Kelvin. Notice that it's just Kelvin and not degrees Kelvin. Now this is something that you need to use on your exam, but you're not actually given. So you need to remember that number, 273.15. Now sometimes when students are using this equation, I find that you get mixed up and you subtract 273.15 when you should be adding it, or you add it when you should be subtracting it. So always go back and double check your answers. Kelvin has an absolute zero. Kelvin cannot be negative. So if you're unsure on degrees Celsius to Kelvin, just remember that Kelvin cannot be negative. And that means because Celsius can be negative, our answer in Kelvin, our temperature in Kelvin, should always be a bigger number than our temperature in degrees Celsius. So that's a good double check to see, did you add it up the right way or subtract it the right way? And just another reminder, no, we've got degrees Fahrenheit, degrees Celsius. This is just Kelvin, not degrees Kelvin. And all of our equations use Kelvin. That being said, a change in temperature is the same in Kelvin and degrees Celsius because remember they've got the same interval. So we're going to deal with that when that arises a little bit later today actually. And just a little bit of a note on those definitions of degrees Celsius and degrees Fahrenheit. They have been refined since the 1700s. The numbers are all roughly the same, but those values are slightly different. So like I think human body temperature is 96.7 degrees Fahrenheit. So they are slightly adjusted there. All right, and now on to the real meat of today's work, the change in temperature. So by the end of this, we should be able to know and use the definition of specific heat capacity. That is something that you've done at GCSE, but we're going to build on it at A level, and it's going to get a bit more complicated. But to start with, they should look like level 3 GCSE questions. During our background knowledge check, you sketched a temperature time graph for heating a pure solid through a liquid to its gaseous form with a constant energy source. If you want to get that out so you can add a couple little notes to it, I would highly recommend that, or you could put this into your notes now. Pause the video now if you need some time to grab that work. So we should have a graph that looks something like this in front of us. It's got a straight line as that solid is being heated, and then it starts to melt, and then that liquid is heated, and then it starts to boil, and then that gas is heated. In practice, we might not look at going from a solid all the way to a gas, but we do look at temperature changes with state changes. So saying we've got -4 degrees Celsius ice from our fridge freezer inside our drink on a summer day, and it heats to 10 degrees Celsius water inside our drink. In order to determine, say, how long that's going to take, we need to have some sort of model. Now, physics is all about using models and representing those models with maths and then interpreting that maths. And that curvy graph that we had before, well, that's going to be really difficult to model mathematically. But those curves aren't very big. So instead of using the curves, we can model that curvy graph with straight lines that pretty much match up with the graph. So then we'll end up with something like this. Rather than talking about this slight curve here, we can say, well, we're just increasing the kinetic energy, the particles are moving faster there, and then we're increasing the potential energy and the particles have potential to make bonds, and then we're going to increase the kinetic energy, and then we're going to increase the potential energy, and then we're going to increase the kinetic energy. And we just deal with these very straight lines. We don't worry about these curves in between the lines because, to be honest, there's not that big of a difference, and this is even me drawing rubbish curves on PowerPoint, and there isn't that big of a difference. So we would expect it to be a good model. In our model, we have heat or thermal energy going into the internal energy of the system in one of two ways. It is either going into the kinetic energy of the particles and increasing the temperature, or going into the potential energy, breaking bonds. But never both of those simultaneously. And that's why we get the straight lines on our graph. We're going to look at those two phenomena separately, and then we'll come back and put them together. So today we're just going to look at increasing the kinetic energy of the particles. And increasing the average kinetic energy of the particles increases the temperature. Recall the idea of absolute zero. And you have done this at GCSE. Just take a moment, maybe pause the video, and think if you can recall that equation from GCSE. So if you give heat to a system or take heat away from a system and it goes specifically into changing the system's temperature, we can calculate that change in temperature, or we can calculate the amount of heat required to do that by using this equation. Q equals mc delta theta. Some subjects and some professors use delta T with a capital T instead of a delta theta, and you'll see why in a moment. So Q is the energy added to the system in joules, M is the mass of the system in kilograms, C is the specific heat capacity of the material, and delta theta is the change in temperature. So sometimes we represent temperature by a capital T, and if you have delta capital T instead of delta theta, that can represent change in temperature as well. That being said, this is how it's written in your physics data sheet, so it's best inside your physics AQA exam to use this form of the equation and not a delta capital T. We'll take a look at some specifics with this equation, and then we'll go over the units that are missing there, the C and the delta theta. As we go through, maybe think of what those units could be. So a few notes on Q. Q is the amount of energy added to the system. It is measured in joules, but occasionally it's given in kilojoules, or even when we're dealing with water, megajoules, because we are dealing with large amounts of energy. Now notice that the definition of Q has the amount of energy added to the system. This introduces a sign notation. If energy is being added to the system, we're increasing the temperature of the system, then Q is positive, and if energy is being removed from the system, or we're decreasing the temperature of the system, then Q is negative. Now this ensures a correct sign convention with the first law of thermodynamics, which we talked about last time, which is essentially just energy conservation, but it is really important that we know this sign notation. I would highly recommend getting this sign notation into your book with maybe a little asterisk next to Q or something, just saying, to be careful about this kind of thing. If we're increasing the temperature, Q is positive. If we're decreasing the temperatures, Q is negative. I'd also make a little note that the units can be given in kilojoules instead of joules, because we are dealing with really large amounts of energy. Like water takes loads of energy to heat up. It takes a lot of energy to make a cup of tea. M is the mass of the system, and like everything else that we do in physics, it's measured in kilograms. But do be careful with this one. It's often given in grams. You really need to watch out for that conversion factor. Sort of everyday stuff is grams, right? If you think about your cup of tea or your cup of coffee, or you bring in a cooler with some ice, we're probably going to have grams and not kilograms. So you might want to put an asterisk next to mass and just say watch out for grams there. In science, we always use Kelvin for temperature, but this equation specifically will allow degrees Celsius because it's a change in temperature. I just want to go through and show you why. So imagine you're calculating a change in temperature from two temperatures, theta 1 and theta 2, and they're given in degrees Celsius. In order to convert between those two, you need to add, between Kelvin and degrees Celsius, you need to add 273.15 to theta 1 and 273.15 to theta 2 to get them into Kelvin. Doing that with our calculation of delta theta gives us delta theta equals theta 2 plus 273.15, all minus theta 1 plus 273.15. Expanding that out, we get theta 2 plus 273.15 minus theta 1 minus 273.15. That negative sign in front of that bracket gets multiplied through both, making both of these terms a negative. But now we've got a plus 273.15 and a minus 273.15, and these two cancel each other out, leaving us with delta theta is theta 2 minus theta 1. So our conversion factor there actually cancels out, and for this equation, delta theta, we can use it in degrees Celsius or in Kelvin. If you're in doubt and you're not too sure, always change it to Kelvin because that's what all of our other equations need to use. But for this one specifically, you can use degrees Celsius or Kelvin. And you might want to make a little bit of a note about that next to or underneath your equation. And it's specifically because it's a change in temperature, and our scale for Kelvin is the same thing as our scale for degrees Celsius. So an increase of temperature in 1 Kelvin is the same as an increase in temperature of 1 degree Celsius. And now finally on to the specific heat capacity. What I'd like you to do is pause the video and use that equation to rearrange for C and then use it to find the units for the specific heat capacity. So correctly rearranged for C, we should have C equals Q divided by M delta theta. And if we just plug in the units on the right hand side of the equation, Q is measured in joules, M is measured in kilograms, and delta theta is measured in Kelvin. So the units for specific heat capacity are joules per kilogram per Kelvin, and written with the superscripts so that it's easier to determine what's in the denominator and what's not. We could equivalently write this as joules per kilogram per degree Celsius because it uses a change in temperature. We could also write this as joules per gram per Kelvin or joules per gram per degree Celsius, or even kilojoules per kilogram per Kelvin or kilojoules per kilogram per degree Celsius. It doesn't really matter, but always keep your units in mind. So it's easier not to change the units of C, so whatever you're given as the specific heat capacity, use those units and change your energy Q, your mass M, and your temperature delta theta to match the units that are given for your C. If you're not given units for C, so like you're calculating C, then I would recommend that you use joules or kilojoules or megajoules, whatever is more appropriate, kilograms and Kelvin. Now these units here are something that you do need to know, and I'd really highly recommend that you do not memorize them. You've got enough stuff that you need to memorize. Don't try to memorize units. This is something that you should very easily be able to work out from the equation, and if you need to, it's going to take you an extra 2-3 seconds on your exam to work out the units from your equation. Okay, please do not memorize them. And just as a little side note, our specific heat capacity is usually given in kilojoules per kilogram per Kelvin, and the reason for that is they're usually quite large numbers. They're usually of the hundreds or thousands, like the examples here. So liquid water, 4,181 joules per kilogram per Kelvin. So if we were to write that in kilojoules instead, it would be 4.181, which is a lot nicer of a number to deal with. So when you are doing questions, always go back and double check. We should have a specific heat capacity of like hundreds to thousands. If you're getting numbers that are tens, that's way too low, you've done something wrong. If you're getting numbers that are like tens of thousands, that's probably too high, you've probably done something wrong. Go back and double check your work. Now, a few limitations on this equation. First of all, we cannot use this for a change in state. It has to be used for a change in temperature. This is really, really important and should be put inside your notes with this equation, that it's only good for a change in temperature and not for a change in state. And the reason for that is that the equation only accounts for the increase in kinetic energy of the particles. It doesn't account for the potential energy or breaking bonds. And sort of to go along with that, the specific heat capacity of different states of the same material is different. To give you an example, ice has a specific heat capacity of 2.108 kilojoules per kilogram per Kelvin. Liquid water is 4.187 in the same units, and water vapor is 1.996 in the same units. So if we were to try and span, say, liquid water over to water vapor, we would actually have to deal with two different specific heat capacities. So we'll get to that eventually, but right now we can't deal with that. And just as a side note, you do not need to know those specific heat capacities. You'll either be given the specific heat capacity and asked to do a calculation with it, or you'll be asked to calculate the specific heat capacity. You don't need to memorize any of those numbers. Another limitation to this equation is that the specific heat capacity of a material can vary for a large temperature difference. So this is a graph of specific heat capacity of ice as a function of temperature. So up the side here we've got specific heat capacity in kilojoules per kilogram per degree Celsius, and across the bottom here we've got temperature. So we can see that at negative 100 degrees Celsius the specific heat capacity of ice is under 1.4, and at 0 degrees Celsius our specific heat capacity is over 2. And that's quite a range in terms of the specific heat capacity. So with this equation, I mean, usually we're just dealing with it over a small amount. So, I mean, if we were to go from like minus 15 degrees to 0, the specific heat capacity doesn't change very much. And saying a value of maybe, 2, 2.1, 2.3, something like that, would actually be fairly reasonable for that section. Remember, physics is about models. So we could model this section as about 2. If we wanted to take a look at, say, going from minus 80 to minus 60, we could probably model that as about 1.6 because it doesn't change much over that. Now, this isn't something that your exam expects you to know, but if you do go on to higher education with anything to do with thermal, it's something that you might want to keep in mind, specifically if you're looking at engineering, that the specific heat capacity actually changes depending on that temperature. Alright, so from that rearranged equation, we can also define specific heat capacity. So this equation is the definition of specific heat capacity, and I'd like you to pause the video and have a practice at changing maths into English. So hopefully in English we have the specific heat capacity is the amount of energy required to increase the temperature of a unit mass of a substance by 1 degree Celsius. Now, this is a definition that you need to know and you need to be able to memorize and give back. A couple things about this definition. It says the amount of energy, and we talked about energy and heat being the same thing. This does actually want the word energy and not heat. Heat is like a okay kind of mark, whereas energy is like a yes, okay? They also prefer unit mass. You can say 1 kilogram, but it is preferred of unit mass. And this 1 degree Celsius, you can say by 1 Kelvin, and either one of those is absolutely fine. They do talk about increasing the temperature, even though this equation works for decreasing the temperature as well. Our definitions are all in terms of the amount of energy added, so we're increasing temperature. So make sure to get that definition into your notes, into your book. Any extra little points that you want about it are good. It should be fairly similar from your GCSE one. I just want to briefly talk about heat capacity. Heat capacity is different than specific heat capacity. So if you're doing any sort of research or reading beyond the syllabus, you might come across heat capacity because it is slightly different. And heat capacity isn't explicitly stated in your specification, but they could give questions to you that have the heat capacity, although they probably wouldn't call it heat capacity. They'd never ask for its definition. They'd only use it inside a calculation. And really, you could tell the difference by the units, so you really need to take care with your units. So we know that the specific heat capacity is the amount of energy required to raise the temperature by 1 degree Celsius per unit mass. The heat capacity is the amount of energy required to raise the temperature by 1 degree Celsius of an object. So they're very, very similar. The only difference there is the mass, right? Where the specific heat capacity is a material property. It depends on the material, whether it's copper, water, wood, whatever. Whereas just heat capacity depends on the object because it takes into account the mass. Mathematically, these two are linked. The heat capacity is the mass times the specific heat capacity, or we could put the heat capacity into our equation that we've been dealing with, where it replaces the MC. So we've got energy is equal to heat capacity times change in temperature. And the units of heat capacity, because it is just energy per unit temperature, is joules per Kelvin. So if they do give you something that's joules per Kelvin and you're looking through the question, you're like, I don't have a mass, I need a mass for Q equals MC delta theta, just double check that they've given you the heat capacity as opposed to the specific heat capacity. In terms of past paper questions, I've only ever found one past paper question that's done this, but it could happen again, it could happen to you. And if you are reading around the subject area or researching around the subject area and going a little bit further into depth, you might come across this, and because the phrasing is so similar, it can be confusing. So don't need to put any of that in your notes, but do keep it in mind anytime you sort of leave the bubble of AQA exam practice. Alright, now we've got a few examples. The way that I would like you to do these examples is to pause the video when you see an example, give it a try, either on scrap pieces of paper or in your notes. In your notes is probably better, so that if you get stuck when you're revising, you can always go back to the example and see how you've done it. And then once you think you've got an answer, play the video through so that you can see the solution. If you are getting stuck, then you can sort of play the video through until you unstick yourself, and then pause the video again and try to get through to a solution. So pause the video now and try example 1. Right, so the first thing that I like to do is to write out what I know, because especially with thermodynamics, there can be loads in different numbers. And as we write them out, we try to do the conversions as well, so we don't get thrown off by those. So we read through it and it says, how much energy would it take to bring a 200 gram pot? We have got a mass of 200 grams, but I don't want grams. I want kilograms. Of water from room temperature, 20 degrees Celsius, so that's our initial temperature, to 70 degrees Celsius, so that's our final temperature. And they did say water, so and at 20 to 70 degrees, that would be liquid. So from our specific heat capacity table there that they've given us, we want to select the liquid water one. So from here, we can use our specific heat capacity question. Q equals MC delta theta. And they are asking us for how much energy. So they are asking what is Q. So our equation's already rearranged. Perfect. We can just plug our numbers in. But hold up, not so quick. We don't actually have delta theta right now. We've got theta I and theta F. And if we were to plug a sum into here, that's not really showing our work because that's not really showing the substitution. So I would either recommend that up here you calculate delta theta as 70 minus 20, which is 50 degrees Celsius. Or what I think is a bit of a better way is we can actually put that into our equation. So we can go theta final minus theta initial. And now we can simply plug our numbers in. And that way we don't have calculations all over the place. It's a lot nicer and easier for our examiner to read. So we've got Q equals 0.200 times our specific heat capacity, 4181, times 70 minus 20. And then we can just put this all inside our calculator. For the purposes of showing your work, you might actually want to show that 70 minus 20 is 50. Sometimes that can be worth a mark, showing that you can calculate that change in temperature. Completely up to you, but sometimes it is worth marks. So we've got Q equals 41810 joules. Now, in terms of significant figures, remember we always round to more than one significant figure. So technically these here are technically one significant figure, but we can read them as two significant figures. So we should be rounding this to two significant figures. Most of the stuff, this would be considered like an A2 topic, an old A2 topic. And most of the A2 stuff is given to three significant figures. Same thing in your exam. It'll probably be three significant figures. But we'll treat this one like it's two. And so we should have Q equals 42000 joules. Or if you'd rather, you can write Q equals 42 kilojoules. A lot of energy to heat up a small amount of water. Example number 2, give the video a pause and try it out. So a block of copper, that tells us our specific heat capacity is 386 joules per kilogram per Kelvin, of mass 47 grams. Remember to convert that into kilograms. At a temperature of 990 degrees Celsius, is cooled to 100 degrees Celsius. How much energy is released? So we go Q equals mc delta theta, and make sure that we either show our calculation of delta theta up here or substitute in final minus initial to show that we're showing our substitution. So Q equals, our mass is 0.047 times C 386 times our final minus our initial. So notice that change in temperature, delta theta, will end up being negative. And if we put that into our calculator, we get negative 16146.4 joules. But again, don't get into the trap of putting so many significant figures. We definitely want to round that to an appropriate number of significant figures, which is, 2 or 3 significant figures. In this case, probably 2, given on the information that we've been given. So that would be negative 16,000 joules, or if you'd rather, you could write that as negative 16 kilojoules, and that's a little bit more eloquent. Now, that negative sign just means that energy has been released. So when it asks us how much energy is released, technically positive 16 kilojoules has been released. The fact that there's a negative sign there just tells us the direction that energy is transferred, and it's transferred out of the system. Now, if you've put a negative sign on your answer line, your exam will allow that. If you put a positive sign on your answer line, your exam will allow that. It's not too fussy with getting this sign correct, because the way that it's phrased, it's actually expecting a positive value, but the way to do it correctly means that your Q value should end up being negative. And if you were to use that with the first law of thermodynamics, which you would be doing in advanced physics, sort of like university level, then you would expect to continue to have a negative number to use in subsequent things. So negative or positive on the answer line, absolutely fine. Example 3, give the video a pause and give that a try. Alright, so the question reads, the power rating of a kettle is 2,500 watts, and 2 cups of water, which is 500 grams or 0.5 kilograms at 15 degrees Celsius are put into the kettle to make some tea. If the kettle is 80% efficient, what is the temperature of the water after the kettle has been on for 1 minute? Now this actually takes into consideration a lot of stuff, and it wants the final temperature there. It takes a lot of stuff into consideration. We need to use the equation linking temperature and change of heat to find our final temperature, but we don't actually know how much heat has been added. So we need to know the useful energy output of the kettle, which means we're going to have to calculate or use calculation involving the efficiency. And in order to find the initial input to the kettle, we need to use the power. So there's a lot here, and if this was actually a past paper question, it would probably be broken down into 3 different steps. The first question would say calculate the energy taken in by the kettle in the 1 minute. And then the second question would say calculate the output or the useful output energy of the kettle. And then the third question would ask you for this final temperature. So it is sort of like 3 different steps to one question. So don't be put off or intimidated by that. So the first bit, we need to calculate the energy that kettle takes in. So our definition of power, energy per unit time. Rearranged energy is power times time. And putting in our numbers, we've got 2,500 times 60 seconds. Remember to convert that to SI units. We need seconds, not minutes. And that gives us an energy of 150,000 joules. A lot of energy. If you want to change this into kilojoules, you're more than welcome to, and you could work through kilojoules. Just be really mindful that you've got that as kilojoules. And the specific heat capacity of water over here is listed as joules per kilogram per Kelvin. So just make sure you don't confuse that later. And then we need to use the equation for efficiency. I'm just going to shorten it to EFF for efficiency like I did there. So efficiency is our useful energy over our total energy. And rearranging that, let's use some proper terms. Our useful energy inside subsequent things is actually called Q, and our total energy, we've already used the letter capital E. So if we rearrange that, we get Q equals E times efficiency. And if we plug our numbers into there, we've got 15,000 times an efficiency of 80%. Remember that means 0.80. And that gives us a Q value of 120,000 joules. Again, we can quote this as kilojoules rather than joules. I'm actually going to move this over to our knowns and then clear it out so we've got some space. 120,000 joules. Alright, so now we can go back and use our Q equals mc delta theta. And if you really want, you can calculate delta theta and then come back and use another equation to link it back to theta. Or you could just plug in what delta theta actually is here. So that's our final minus our initial temperature. And we want to rearrange for that final temperature. So we divide both sides by mc, and we get our final temperature minus our initial temperature is equal to Q over mc. And then we add our initial temperature to both sides, and we get that our final temperature is equal to Q over mc plus our initial temperature. Plugging in our knowns, we've got 12,000 over a massive 0.500 times the specific heat capacity of water, 4181, plus our initial temperature of 15 degrees Celsius. Now, if you did convert this into kilojoules, just be careful that you also convert this into kilojoules. So if you have this as 120, then this should be 4.181. And if we plug all that into our calculator, being careful of the fraction and the plus after the fraction, we get a final temperature of 72.40 degrees Celsius, but rounded to a correct number of significant figures, 72 degrees Celsius. Now this is a slightly different example. It's spot the mistake. So I'm going to work through this problem, and this is an example of what not to do. And I want you to see if you can find the mistakes. There are 5 of them. So when you think you've spotted one, just jot it down on a little piece of paper. If you need to pause the video at any time, go for it. And if you haven't spotted all 5 by the end, then pause the video and see if you can look at the working and see what's wrong. Alright, spot my mistakes. So writing out what I know first, how much heat is required to bring 1 litre, ooh, that's a volume, of water initially at 75 degrees Celsius to 120 degrees Celsius. And they've also said water. The density of water at 75 degrees is 975 kilograms per cubic meter. And they've asked us for how much heat, how much energy is required. So the first thing we need to do is find out the mass, and we can do that from our density equation. Density is mass per unit volume, which means mass is density times volume. So our mass is equal to 0.001 times 975, which gives us 0.97, whoops, that's a 7, 75 kilograms. And then we can use our heat equation, Q equals mc delta theta. So Q equals 0.975 times 4181 times 120 minus 75, our change in temperature there, and that gives us Q equals 183,441. Awesome. Can you spot the 5 mistakes here? So usually the first 2 mistakes that are spotted is someone goes, miss, sig figs. Yeah, okay. Q equals 1.8. Well, technically we should just have 1 sig fig with that volume, but we'll use 2 because we should never round to 2. So Q equals 180,000. Yeah. And usually the second mistake that people go is they go, units, because I get you so ingrained of thinking about the unit. So we've got 180,000 joules, or we can say 180 kilojoules, and that solves 2 of our problems. We've got a sig fig problem there and a unit problem. The other 3 tend to be harder to find. Now 2 of them are the same mistake done in 2 different places. One of the places is here, and one of the places is here. In both of these, we would not get a mark for our substitution. So in this first one up here with m equals rho v, we've actually substituted them in the wrong way. This 0.001 is our volume, and this 975 is our density. So when we write these in, our numbers should follow the same order as our letters. So if we're going to write m equals rho v, this should be m equals 975 times 0.001. So if you were getting marked on showing your work, you would not get this substitution mark. You would lose marks for that. Similarly down here with the Q equals mc delta theta, you've got one term that magically turns into 2 terms, and you can't do that inside a substitution. You either need delta theta turning into a singular number of 45, or you need to have delta theta turn into our final minus our initial, and then show the substitution of those numbers into theta f and theta I. The third one here that hopefully you guys caught, because this is the whole point of this one, is that going from 75 degrees Celsius to 120 degrees Celsius, water doesn't stay as a liquid. It goes from liquid water to water vapor or gas. And this equation only works for a change in temperature, not to change in state. If we were to heat up our water from 75 degrees Celsius to 120 degrees Celsius, we would also be undergoing a state change. So all of this, well, not all of this, is absolute bogus because it doesn't include that state change. Hopefully you found all 5 of those. So now this is quite a long video, but we're just going to run through some key concepts that we've covered earlier. Temperature is a measure of kinetic energy of the particles. And this gives us rise to the idea of absolute zero, 0 Kelvin, being no kinetic energy. To convert from degrees Celsius into Kelvin, we add 273.15. You need to memorize this number. We can model heating substances as increasing temperature or a state change, never both together, or at least not for now. And for changing temperature, Q equals mc delta theta. Remember that Q is positive for adding energy and negative for removing energy. Remember to be careful with units for this. Q is often given in kilojoules, which is fine as long as you remember it's in kilojoules. Mass is often given in grams, which must be converted to kilograms. Our specific heat capacity is again often given in kilojoules per kilogram per Kelvin, and that kilojoules, as long as it works with the energy, you keep that in mind. And that delta theta, because it is a change in temperature, we can use that in degrees Celsius or Kelvin. And the definition of specific heat capacity is the amount of energy required to increase the temperature of a unit mass of a substance by 1 degree Celsius. Now I know it's been a really long video, but I've got one more thing I'd like you to do, and that is a past paper question. What else? So give the video a pause, try this past paper question, and then play the video and you'll be able to see the mark scheme. When you can see the mark scheme, mark your work and see how well you did out of 6. So here's the mark scheme. Hopefully you got 6 out of 6, and that is the last thing. Have a fantastic day.